Karl Popper's work, The Logic of Scientific Discovery, first published in 1934, remains one of the most influential texts in the philosophy of science. In this book, Popper challenges the prevailing views of scientific methodology, most notably the inductivist perspective that had dominated scientific thought for centuries. At its core, Popper's philosophy emphasizes falsifiability as the key criterion for determining whether a theory is scientific or not. His approach not only sought to revise the notion of science but also to clarify the demarcation between scientific and non-scientific claims. Inductivism and the problem of induction. The dominant view of science prior to Popper was inductivism, which asserts that scientific theories are derived from observations of the world. According to this view, repeated observations of phenomena allow scientists to make generalizations, and these generalizations can be considered as theories that represent truths about the world. This idea was rooted in the philosophy of empiricism and was especially influenced by figures like David Hume and John Stuart Mill. Hume, in particular, highlighted the problem of induction, suggesting that no amount of observations can ever prove a theory with certainty. From his perspective, just because the sun has risen every day of human history, there is no logical guarantee that it will rise tomorrow. Popper, in contrast, rejected inductivism outright. He argued that induction, as a method for discovering scientific truth, is logically flawed. Even though we may observe a phenomenon repeatedly, such as the sun rising, this does not justify the belief that it will always rise in the future. Popper's critique of induction was rooted in his understanding of the limits of human knowledge. While observation can lead to hypotheses, it cannot provide conclusive proof for any theory. For this reason, Popper proposed falsifiability as a criterion for distinguishing scientific theories from non-scientific ones. Falsifiability as the demarcation criterion. Falsifiability, in Popper's framework, refers to the idea that for a theory to be considered scientific, it must be capable of being proven false by some conceivable observation or experiment. A theory that cannot, in principle, be refuted by any observation is not scientific. Popper's emphasis on falsifiability marked a sharp departure from the view that scientific theories could be verified through repeated observations. An example of a falsifiable theory would be the claim that all swans are white. This statement is falsifiable because it is possible to observe a black swan, which would directly contradict the theory. Conversely, a statement like there are invisible and undetectable fairies in the garden is not falsifiable because there is no conceivable observation that could disprove the existence of such fairies. The impossibility of falsification places this kind of claim outside the domain of science. Popper's view also has implications for how scientific knowledge progresses. Rather than accumulating observations to confirm a theory, science advances by testing theories rigorously and attempting to falsify them. When a theory is falsified, it is either rejected or modified, and the scientific process continues with the aim of finding better, more robust explanations. The role of hypotheses. In Popper's philosophy, the role of hypotheses is central to the scientific process. Hypotheses are not simply tentative guesses based on observations but are bold conjectures about the nature of reality that must be subjected to rigorous testing. A good hypothesis is one that makes predictions that can be empirically tested and potentially falsified. If a hypothesis survives testing, it is not considered proven, but rather it is regarded as a theory that has not yet been falsified. The role of experimentation in science, therefore, becomes crucial for Popper. Scientists create experiments designed to put their hypotheses to the test, actively seeking to disprove them. This approach is a departure from the more passive approach of gathering confirming observations. Instead, Popper's methodology insists on the active role of critical testing and refutation in the advancement of science. Popper also argued that scientific knowledge is provisional. Since no theory can ever be definitively proven true, it is always open to revision or rejection based on new evidence. This contrasts with the traditional view of science, where the goal is to confirm theories and build knowledge based on accumulated facts. The problem of confirmation and the problem of demarcation. One of Popper's key contributions is his rejection of the concept of confirmation. In the traditional view of science, confirmation is seen as the process of gathering evidence to support or verify a theory. However, Popper argued that no amount of confirming evidence can ever establish the truth of a theory. Even if a theory is consistent with all observed facts, it is still possible for new observations to come along and falsify it. This idea is sometimes illustrated by Popper's famous example of the theory that all swans are white. Even if we observe 1,000 white swans, there is always the possibility that we will encounter a black swan, thereby falsifying the theory. Popper also addressed what is known as the problem of demarcation. This problem involves distinguishing between science and non-science, or what he referred to as pseudoscience. The issue of demarcation was particularly relevant during Popper's time, when many pseudoscientific theories were being presented as legitimate scientific theories. Popper argued that pseudoscience cannot be considered science because it does not make falsifiable claims. For instance, astrology, Marxism, and Freudian psychoanalysis were examples of what Popper considered pseudosciences, as they could not be meaningfully refuted by observation or experiment. By focusing on falsifiability as the criterion for scientific theories, Popper established a clear line of distinction between science and pseudoscience, which has been widely accepted in the philosophy of science. The growth of knowledge and scientific revolutions. Popper also tackled the issue of how scientific knowledge grows over time. In contrast to the gradual accumulation of facts envisioned by inductivists, Popper saw scientific progress as occurring through a process of trial and error. According to Popper, scientific knowledge grows through the formulation of bold hypotheses, the testing of those hypotheses, and the eventual refutation of incorrect theories. When a theory is falsified, scientists seek out new theories that offer better explanations. Over time, this process leads to the refinement and improvement of scientific understanding. In his later work, Popper introduced the idea of scientific revolutions, which are periods of rapid change in scientific understanding. These revolutions occur when a dominant scientific theory is overthrown by a new theory that better explains the phenomena in question. The most famous example of a scientific revolution is the shift from Newtonian mechanics to Einstein's theory of relativity, which fundamentally changed our understanding of space and time. Criticism and legacy. Popper's ideas have not gone without criticism. Some philosophers have pointed out that not all scientific theories are falsifiable in the strict sense, particularly in fields like mathematics or theoretical physics, where some propositions may not be directly testable. Others have questioned whether falsifiability can always serve as a clear-cut demarcation criterion, given the complexity of scientific theories. Despite these criticisms, Popper's influence on the philosophy of science is undeniable. His work has had a profound impact on how scientists, philosophers, and the public understand the nature of science. By insisting that science is about bold conjectures and rigorous testing, Popper contributed to a more dynamic and open-minded view of scientific inquiry. His ideas have shaped the way we think about the scientific method and the limitations of scientific knowledge. In conclusion, the logic of scientific discovery provides a rigorous framework for understanding the process of science. Popper's emphasis on falsifiability, critical testing, and the provisional nature of scientific knowledge has influenced not only the philosophy of science but also the practice of science itself. His work challenges us to think critically about the claims we make and to recognize that the quest for knowledge is an ongoing and imperfect process.